Okay, so the next one in your notes, let's get some practice actually trying to use a ray tracing diagram to solve a problem. Okay, and then we'll jump into using the equation. So ray tracing diagrams are a good tool. Sometimes they can tell you everything you need. The equations are good too. Sometimes you use one to check your work for the other. Realistically, the equations are less work, but there's something very satisfying about a good ray tracing diagram. So we have a student's face that's 30 centimeters long. So that is going to be the height of our object, right? Their face is actually that long. The student stands 40 centimeters away from a concave mirror. So that is the distance of the object. That's the distance between the object and the mirror with a focal length of 28 centimeters. So that's our focal length, okay? Okay, so I'm going to set up my ray diagram. I draw my principal axis, okay? Now you don't need to be super exact, okay? Again, ray diagrams, as long as you do it somewhat reasonably carefully, you should get the right result. But take care with stuff like making sure your focal point is half of your radius of curvature, okay? So for example, I'm going to say my focal point is 5 centimeters. Notice how I measure it out, which means is 5 centimeters from the vertex, which means my center of curvature will need to be another 5 centimeters. So 15, so 10, so then 5. Okay, that part's pretty important. Okay, honestly, other than that, not too much. Other than that, you don't need to be super careful about other stuff, okay? We just need to do it reasonably well and we should get the right result. Okay, so the student stands 40 centimeters away from a concave mirror with a focal length of 28 centimeters. So if this is 28 centimeters, what length is this, right? If this is 28 centimeters, if we're calling this 0, then that's 28. Well, then this must be 56, right? Center of curvature is always double the focal length. Okay, so our object, we're just going to simplify it as an arrow. They're 40 centimeters away. So they're between 28 and 56, right? They're between the focal point and the center of curvature. So what does our table say? Well, it says if you're between the focal point and the center of curvature, right? So radius, so you're between the radius and the focal length, okay? You should get an enlarged, inverted, but real image. So we're expecting something that's bigger, that's forming on this side of the mirror so that it's real, and that is upside down. Let's see if our ray tracing diagram predicts that. So anywhere between here, we should get that result. So 28, 56, again, don't need to really be super careful here. You just need to make sure you're between them. Okay, we're going to follow our P, F, C. Okay, again, P and F are enough. C is a good check. So the P is for parallel. Okay, so the first one goes parallel to the principal axis and then through the focal point. So parallel to the principal axis and then through the focal point. Next one goes to the F. Okay, so now the F is focal point. So it goes through the focal point. It reflects now parallel. Okay, so really the first two are the other ones backwards, right? Parallel, then through the focal point, and then through the focal point, and then parallel. So you'll notice here, this happens a lot when you're drawing ray tracing diagrams. I just need to make that one longer. That's okay, right? They can still intersect. So they can still intersect. See what I mean? Without a ruler, this would be a nightmare, okay? So realistically, we now know where our image is going to be, okay? It should be, since 2 rays left the top of the arrow and 2 rays here, if our eyes were here, we would be saying, hey, I see 2 rays that come from the top of an arrow. There must be the top of an arrow here, right? And you would. So there should be, we already kind of know that our image is going to be formed here, but we can check our work with that C, with the third one, which says that any ray through the center of curvature, will get reflected back along the center of curvature. So if any ray that we're going to pass through the center of curvature, right? Now, I know there's no mirror over here, but if this were a whole circle, that rule has to apply still, right? So you can imagine, essentially what we're going to end up doing on this rule always is just kind of drawing a ray through the center of curvature, straight line through the center of curvature. Now, again, that's not perfect, but you can see what I mean, right? We are very close on our center of curvature. That third rule is essentially just a check, okay? If the question asks you to fully actually determine the height of the object or the distance just using a ray diagram, then yes, you will need to be careful. You need to actually measure out not the numbers themselves, But the ratios, right, that would need to be careful about that. But since we're just trying to determine what kind of image would be formed, that works fine for me. Notice, what were we expecting? According to our table, we were expecting real. Aha, it formed on this side of the mirror, so it's real. Okay. We were expecting enlarged. Yep, we definitely got it looking enlarged. And we were expecting inverted. Yep, we got inverted. So just from our ray diagram, we got that the image type is real because it's the true side of the mirror that actually exists. Notice how these are real light rays that are converging to form the image, not dotted fake ones. Okay, image attitude, inverted. Image size, that's definitely bigger than that one. Okay, and image location. Image location. Now for that, we would either have had to draw a very, very careful diagram, or realistically, you're always going to use your equations for stuff that is actually asking us for a number. Okay, so the image location, I guess you could say, is in front of mirror, but let's go get an actual number now. Let's jump into using those equations. Okay, so let's see if we can confirm what we saw in our ray tracing diagram with the mirror equations. So these equations look weird because they have a lot of reciprocals in them, but really the math in them is not that bad. Once you realize that you can just flip it by putting it to the power of -1, right? Which your calculator will let you do. Okay, so our ray diagram told us again that we would get a real, inverted, enlarged image. Let's see if the math tells us that as well. So using our mirror equation, okay, so 1 over the focal length equals 1 over the distance of the object from the mirror plus 1 over the distance of the image from the mirror. So we are looking for the image location. In other words, where does the image appear to be? That's the distance of the image, right? So that's what we're looking for. So to get that by itself, ask ourselves what's happening to it. Why is it not alone? Well, 1 over DO is being added to it. So let's just subtract 1 over DO from both sides. And we have 1 over F minus 1 over DO equals 1 over the distance of the image. There we go. Now, we want the distance of the image. We don't want 1 over the distance of the image. So how do we flip that? I mean, we could multiply and then divide them, but that's going to get ugly. Why don't we just do this? Take it to the power of -1, right? Something to the power of -1 is just that flipped. So then, okay, now don't make the mistake of flipping both of these, of saying, okay, F minus DO. No, right? That's not the same thing. So for example, 1 over 2 minus 1 over 4 gives you 1/4, right? 1 over 4. That is not the same thing you get if you flip 2 minus 4, right? If you do 2 minus 4, you get -2. Flipping that isn't going to give you a positive 1/4, okay? So don't make that mistake. What this just means is we can flip this side, so now we have DI equals, and just leave it like that. You can punch that in your calculator. There's nothing wrong with punching that in your calculator. You have a to the power of button, you have a negative and a 1 button, so you can punch that in. So DI equals 1 over the focal length was 28 centimeters. Units here are okay as long as everything's the same. Don't mix centimeters and meters, but if everything's in centimeters, there's nothing wrong with that, okay? Because we're not actually multiplying anything here. So minus 1 over DO. So the student is 40 centimeters away. And then we're going to flip that. So we're going to do 1 over 28 minus 1 over 40. And then when we get our answer, we're going to do 1 over that. Okay, or you can do to the power of -1. And so the distance of the image is 93.3 cm. Or to 2 sig digs, it's 93 cm. Now, what does that positive mean? Because it means something. We would have got a negative. We could have got a negative. That's possible. Okay, but we got a positive. So remember, that means the image formed in front of the mirror. Sure enough, yes, our image did. It formed in front of the mirror, on the real side of the mirror. So in a way, this tells us two things. DI, yes, it tells us the image location, but it actually also tells us real or virtual. So we got positive, so yes, real. Okay, we'll just put it in blue to show that our equation does confirm it too, right? It's positive, so that means real. Now to figure out if our thing is inverted and or enlarged, we need to go to the magnification. So remember, if the magnification is bigger than 1, it's enlarged. That's just essentially saying how much we're multiplying its height by. And if its magnification is negative, that means we're flipping it. So then it would be inverted. So we can figure out, okay, so magnification equals, if you look on your data sheet, yes, magnification equals H image over height of object, but it also equals negative DI over DO. So the magnification equals negative. Our DI is 93.3 cm, okay, over our DO was distance of the object was 40 centimeters. So the magnification is, if you do negative 93.3 over 40, you will get negative 2.3325x. Okay, what does that negative tell us? That negative tells us it's inverted. And this number is bigger than 1, so it's enlarged, right? It's 2.3325 times bigger, except we can't actually say that because to 2 sig digs, all we can really say with precision is it's 2.3 times bigger. So enlarged, we'll say magnification equals negative 2.3x. Okay, the x means time, it literally means time, so like 10x would be 10 times bigger, okay? And it's inverted, yep, checks out. It's inverted because we got a negative magnification. If we wanted to know how big their face would appear, we could take the other version. We could say m equals hi over ho. No negatives this time, be careful, look at your formula sheet. Okay, so times ho, which makes sense, right? Never just trust a formula blindly. Does it say something that makes sense? Remember, magnification is how many times bigger does it make it look? So we're saying that the height of the image will be the height of the object times m, right? Times the magnification. So height of the image will be, height of the object was 30 centimeters times 2.3325, and you get that the height of the image, sorry, negative 2.3325, and you get the height of the image is negative 70 centimeters to 2 sig digs. Okay, if we wanted that information, which the question actually didn't ask us for. So what does that negative mean? It means it's below the principal axis. It's inverted, it's down. Okay, so remember, again, if we're doing our coordinate system kind of, everything over here is a positive d, right? If it's up here and up here, it's positive, right? So it's positive, positive. This would be a negative d, but a positive height, right? Down here would be a negative height and a negative d. And over here would be a positive d because it's on the right side of the mirror, but a negative height. So the first one is for d, the second one is for height. Always for the image because the object is always positive. Height and distance, that's how we define the positive direction. Okay, now this one, I would say this would normally be a white. Now this one I would usually say go to the whiteboards, do the ray tracing diagram yourself. I'm not even gonna actually do the ray tracing diagram, at least on paper, on video. I will post, when I post the notes, I'll do it, sure. But you know what? It's actually the exact same one because they're between the focal point and the center of curvature. So I don't see the point in doing that. Okay, I'm just going to say, let's just try our math this time. Let's just see how if we can just rely on our equations for this one. A child is standing between the focal point and center of curvature of a concave mirror. So that's important. Yes, we've only done concave, but you need to read carefully. Okay, concave mirror. So right away, honestly, maybe even just write that so you know. Okay, they see that their face is upside down. Ooh, they see that their face is upside down. What does that mean for our image? What does that mean for our image? It's inverted. It's upside down. Okay, it's going to have a negative height and 47 centimeters long. They keep using that word long. I wish they used tall, right? That would be hi. Be careful, right? They see that their face is that. So the child is amazed because their face is only 18 centimeters long. So that's h of the actual object that's being reflected. Okay, we don't know the answer to these ones. This one we can figure out just on our own, but let's go ahead and try it. We go to write our givens, okay? If the height of the image is 47 centimeters, but it's inverted, how should I approach that? Well, I should say that hi, yes, equals 47 centimeters, but remember, if it's inverted, it's negative 47 centimeters, right? Child is amazed because their face is only 18 centimeters long, so they're amazed because the height of the object should just be 18 centimeters. Now, since we have both of those things, let's go ahead and just bang off the magnification right now, because that's enough to tell us, right? So magnification, again, this is from your data sheet, equals the height of the image divided by the height of the object, right? The ratio of how big it looks compared to how big it actually is. So equals negative 47 centimeters over 18 centimeters. And so the magnification I got is negative 2.61111 times, right? 2.6111x to 2 significant digits. The magnification is negative 2.6x. So it looks 2.6 times bigger, and the negative means it gets flipped. Okay, so boom, look at that. We've already answered. What is the magnification of the image? Negative 2.6x. Is the face erect or inverted? Yeah, the question told us it was inverted, but now we know it's definitely inverted because we got a negative magnification. Is the image virtual or real? How do we do that with math? What do we have to find? Well, we have to figure out, remember, virtual forms behind the mirror, real forms in front of the mirror where the object is on the same side. So we essentially just need to figure out, is the image distance negative or positive? If it's negative, it's behind the mirror and it's virtual. If it's positive, it's in front of the mirror and it's real. So in other words, we need to find di. Now, we can't use 1 over f equals 1 over do plus 1 over di just yet anyway. However, notice on your formula sheet, if you look at the magnification, the mirror equation, under the waves section, right? So you'll notice that m is equal to hi over ho, but it's also equal to negative di over do, which means that hi over ho is equal to negative di over do. Yes, I could use m, but that was a calculated value, so let's just play it safe and use the ones the question already gave us. Okay, so I can multiply both sides by do. I'm just going to do by negative do if that's okay, because then the negative cancels and so does the do. So negative do. Then we have that the distance of the image will be negative do hi over ho. Okay, now we have all those things, right? If they are standing 1 meter away from the mirror, so do equals 1.0 meters. Okay, so equals negative 1 meter times the height of the image, which we're told was negative 47 centimeters. That negative doesn't go away, divided by the height of the object, which we know is 18 centimeters. And so the distance the image appears to be away from the mirror is going to be negative times a negative is a positive. So I got 2.6 meters. Makes sense, right? It's essentially the same thing. Notice how I could have used m too. I could have done m times di, right? M could have been equal to this. Would have got the same answer. Okay. Notice that's positive. So what does that positive tell us? If the distance image is if the image distance is positive, right? Is that a virtual image or a real image? Well, if it's positive, it means the image is forming on the real side of the mirror, on the front side of the mirror, right? So it must be real. Okay. Now, if they are standing 1 meter away from the mirror, what is the focal length of the mirror? So now that we've got our di, we can use that 1 over f equals 1 over di plus 1 over do. And there we go. We don't have to manipulate too much other than this. So f equals 1 over 2 point. It actually is repeating 1, 1, 1, just like before. Okay, cm plus 1 over the distance of the object, which was 1 meter again. Okay, so do 1 over 2.6111 plus 1 over 1, which is just 1, and then do 1 over your answer, or do your answer to the power of negative 1. And you get that the focal length is 0.72 meters, or 72 centimeters. Whoops, this wasn't centimeters, this was meters, which is good, because if it had been centimeters, I couldn't have mixed them like that, right? So that was a mistake in writing centimeters, but if it hadn't been a mistake in writing centimeters, then I would need to go back and change the math. So there we go. We got focal length. We got all that stuff. Okay. Okay, so I'm actually just going to ask you to jump a little bit ahead in the notes. Usually this would kind of be all mixed together. That's why it's like this. However, for offsite, I'm kind of trying to keep today about concave. So we'll just do all the concave ones that appear in the notes. So a 2 centimeter toy is placed upright beyond the radius of curvature of a concave mirror. Okay, concave, so that's important. Well, where will the image of the toy be formed and how will it appear? So where will the image of the toy be formed and how will it appear? So let's try and solve this with a ray tracing diagram, because this gives us a little bit of a different result than the last two. So it's good to see that. Okay, so I'll switch over to paper so you can see me solve it up that way. So it's essentially just asking us, where will the image of the toy be formed and how will it appear? So this is attitude, right side up or upside down, right? And magnification. So enlarged or diminished, where will it be formed? That's essentially asking, okay, that kind of is asking for DI. So we could calculate DI or we could ray diagram it. So I'll just set it up with my principal axis and all that. Okay, so the toy is placed upright beyond the radius of curvature. So it's even farther than the center here. So I'm going to go ahead and draw the object. Okay. And then I'm just going to follow PFC. So first parallel and then through the focal. Parallel through the focal. Okay. Then the opposite of that, focal parallel. So PFC, so now through the focal. and it reflects parallel. And technically, we already know where our image should be, right? It should be right there where those two intersect. Let's just do do our C to check. So a ray through the center of curvature will reflect right back. Look at that. Perfect. So now that I've done that check, okay, it hits the mirror if the mirror kept going, and it reflects right back the way it came. And look at that. Definitely we have an image there. That one worked out real well. Okay, so we can answer this question just with a ray diagram. Where will the image form? Well, between the center of curvature and the focal point. So beyond the radius of curvature, no. Okay, B, C, and D all say the same thing. It will appear inverted. Yeah, inverted. So this one says it will appear upright. So it's down to B or C. Now, is this thing diminished or enlarged? Does it look smaller or bigger? Okay, that one's a little tougher to tell, but it is definitely smaller. It's definitely not bigger. Okay, inverted with size less than 2 centimeters because 2 centimeters was the height of the object. But to check with our mirror equations, we're going to have to do a little bit of thinking right off the bat. Okay, so remember the radius, okay, where the center of curvature is. So where the center of curvature is, the radius of curvature is by definition twice the focal point, right? It's 2 times the focal point. So the reason that we are saying that is because we need to plug something into this equation so that we can do some cancellation to get it to work out, right? We need to write one variable in terms of another variable. So all it told us is that it's placed beyond the curvature of a concave mirror. So beyond R is 2F. So let's just make up a number. You can do this. So let's say DO equals, how about 3F? That's definitely bigger than 2F. So this is now beyond the radius of curvature, right? If this is 2F, then 3F is somewhere over here, and that's where we'll put our object. Okay, so what does that let us do? It lets us say 1 over F equals 1 over DI plus 1 over DO, yes, but DO equals 3F. See what I mean? Now we'll actually be able to get DI in terms of F, because that's what we need to know. We need to know, based on this multiple choice, where is it relative to the focal point? So subtract 1 over 3F, subtract 1 over 3F. And so we have 1 over F minus 1 over 3F equals 1 over DI. Okay, now be careful. Don't forget your grade 8 math here, right? This is where students sometimes trip up, but it's not because of physics 30. It's because of math 8, okay? 1 over F minus 1 over 3F. You can't subtract those until you have a common denominator, okay? So the easy way to get a common denominator, multiply by a fancy 1. When I say a fancy 1, I mean something that's going to make you have the same denominator without changing the number, right? Because that way you didn't change the number, so you didn't break any rules, but you get it into a form you need. So the fancy 1 I see here would be 3 over 3, right? 3 over 3F is the same as 1 over F, because those 3's could just cancel out. So we haven't changed anything, so we have 3 over 3F minus 1 over 3F equals 1 over DI. And there we go. Now we are allowed to subtract those, so we actually have 2 over 3F equals 1 over DI. And now I can just go ahead and flip them. And what do you know? DI equals 3F over 2, or 3 over 2F. In other words, 1.5 F. So if DI is 3 over 2F, it's 1.5 F. Is it beyond C? Right? This is F. This is 2F. If it's 1.5 F, right, here is DI, like our ray diagram predicted. Yes, okay. So there we go. So that tells us that F is smaller than DI, because DI is 1.5 F, but DI is smaller than the radius of curvature. Like we did our ray diagram, we can now eliminate A. However, we can't eliminate B, C, or D just based on where the image is. We need to figure out how the image will actually appear. Will it be bigger, and will it be erect or inverted? But we have DI, and we know that the magnification is equal to negative DI over DO. So the magnification is equal to negative. We have DI in terms of F, and we have DO in terms of F, which means we can probably do some calculation here. So we'll go here, okay, M equals negative DI. Well, DI we just found if we make DO 3F, which we're allowed to because all that determines how the image forms is where it is relative to those things, Okay, so we could make it 3, 4, 5, 6, 10f if we wanted, as long as we say we're beyond the center of curvature. So negative 3 over 2 f was di over do we said was 3f. And look what I mean. So f, those cancel, and we get that the magnification is equal to negative 3 over 2 over 3, which is equal to negative 3 over 2. Dividing by 3 is the same as multiplying by 1 over 3. So that equals negative 3 over 6 equals negative 1/2. So if our magnification is negative 1/2, the negative tells us it's inverted. The 1/2 tells us diminished, right? It's going to look half as big as it should. Now, remember, we just made that number up. So we don't actually know how far it is beyond, but all we were trying to figure out is what do objects look like when they're reflected from beyond the radius of curvature. So what do we say? Diminished and inverted. So size greater, not B, appear inverted and diminished. There we go. C is our guy. D is wrong because it says enlarged. Now, for example 5, if an object is placed at the focal point in front of a concave mirror, where will the image be formed and how will it appear? So again, memorization can help you, right? Sometimes memorization is your friend. To me, though, memorization is never the friend of true understanding, okay? So test tip, you might want to memorize because it just makes it go faster. Life tip, understanding, learning tip, see if you can work it out with the math and just with your ray diagrams. So if an object is placed at a focal point in front of a concave mirror, where will the image be formed and how will it appear? So I'm not saying don't memorize. I'm just saying don't only memorize. Know how to do these diagrams as well, okay? Because realistically, when I say that, when I read that, I know the answer. If it's at the focal point, no image formed, okay? And you saw that when I had the mirror here, right? Okay, so now, okay, our object is at the focal point. It's right there. Okay, so let's draw 2 here. The focal point rule is a little weird to do here, right? Because it's kind of going straight down. So let's just try doing our P and our C. We could even throw in our V. So parallel and then through the focal point. Okay, now let's just do our center one. So it will, okay, reflect back through the center. Notice how parallel these 2 lines are. What do we know about 2 parallel lines? They never intersect. So these are never going to intersect, which means they'll never converge, which means we'll never get an image formed, okay? Same for if I do this little one that's a little bit trickier to pull off because you have to estimate, but, right, notice that if I make the angle of incidence equal to the angle of reflection, aha, that one too, parallel. 3 parallel lines that will never meet. And so no image will be formed. The image will be formed at infinity. It will never be seen. It's always true when you're at the focal point of a concave mirror. Okay, let's see if we can use the math to back us up on 5 from our ray diagram. So remember on our ray diagram, it gave us B, said the image will be formed at infinity. Can the math back us up here even? You bet. So let's see. We have 1 over f equals 1 over di plus 1 over do. Now we're saying that the distance of the object is f, right? The distance of the object is the focal point. So 1 over f is the focal length, sorry. 1 over di plus 1 over f. Now look at this. 1 over f equals 1 over di minus 1 over f. Let's solve this for di like we wanted. So minus 1 over f minus 1 over f. Do you see what's happening here? 1 over f minus 1 over f equals 1 over di. What's 1 over f minus 1 over f? 0. So 0 equals 1 over di. There is only one number that you can put in and get 0. 1 over something, and it's not even a number, it's a concept, right? 1 over even 10 quadrillion is not 0. It's 0.0000001, but it's not 0, okay? If 1 over di approaches 0, then di approaches infinity, okay? So from that, we would say di equals infinity. Ugh, you shouldn't say anything equals infinity. That's bad. So if you're looking for practice with this stuff, which I do really recommend you try drawing a few ray diagrams, try especially since these are new equations as well. Okay, check the agenda or the Google Classroom for which ones go with this stuff.